Howdy, howdy, this is Mr. Potter. Today we're going to be talking about limits involving infinity, both the limits that go towards positive and negative infinity in the x direction, and positive and negative infinity in the y direction. And these will help form the horizontal and vertical asymptotes that we're familiar with from our previous pre-calculus classes. So we're going to start with a couple of familiar functions. We've got the function for y equals 1 over x, our reciprocal function. And we know that this graph tends to have this general shape in the first and third quadrants. What's important to note is that as we go to x increasing without bound, as x goes to infinity, this function tends to go to 0. The y value gets closer and closer to the x-axis. And similarly, as the limit as x goes to 0 from the positive side of my function is going to infinity. This is one of those where it's increasing without bounds. Sometimes you'll see the use of the does not exist, but we tend to not use that if we can say for sure that it's headed towards a positive infinity or a negative infinity. That more specific answer is the preferred answer. Now, in a similar aspect, when I look at the third quadrant of this, if I look for the limit as x approaches 0 from the negative side of my function, I notice that this is also going towards negative infinity. And as x decreases without bound, as x approaches negative infinity, my function goes to 0. These are behaviors that I notice from the parent function of y equals 1 over x. And similarly, I can talk about the parent function y equals 1 over x squared, the reciprocal square function. This gives us behavior in the first and second quadrants. Again, I still have the same asymptotic behavior. The only one of these limits that are different is the limit as x approaches 0 from the negative side. And that's the fact that it goes to a positive infinity. And so this brings up an interesting idea. Here, if I want to talk about the limit as x approaches 0 of 1 over x, I definitely would have to use the does not exist, because 1, it does not approach a particular value, and 2, the infinities that I'm approaching, positive if I'm in the first quadrant, negative if I'm in the third quadrant, don't even match. Whereas here, if I wanted to talk about the limit as x approaches 0 of 1 over x squared, I'm perfectly fine saying does not exist, but I would not be in error if I said that this was infinity, because the left and right sides both approach the same infinite value. They both increase without bound, where I don't have that necessary behavior for the 1 over x function. And so this is just a little something to talk about when the AP uses context of saying a limit is non-existent, or if a limit is positive or negative infinity. The fact that it does not exist is perfectly correct, and if that choice is available, it'll be the only choice available, but we do need to be aware of situations where, in the case of, say, 1 over x squared, the fact that as x approaches 0, these both increase without bound, so it'd be perfectly fine saying this limit is infinity instead of using the does not exist. I want to deal with this parent function behavior as I talk about limits as x approaches infinity. So if I was to say that the limit as x approaches infinity of f of x is equal to b, or the limit as x approaches negative infinity of f of x equals c, then y equals b or y equals c is what we would call a horizontal asymptote. And so it is very easy for me to think of a function that would have some type of behavior like this, where I could have one horizontal asymptote as x increases without bounds, and a different horizontal asymptote as x decreases without bound. So I do need to take into consideration both of these limits as x goes to infinity and as x goes towards negative infinity. And this is how I determine if a function has a horizontal asymptote. So let's go through a couple of examples. I've got this example, y equals 2 plus 1 over x. And if I look at the limit as x approaches positive infinity of my function. I remember from the parent function behavior of 1 over x that this goes to 0 as x increases without bound. So this limit ends up being 2 plus 0, or 2. And so that means that I have a horizontal asymptote at the equation y equals 2. But I do also need to consider the limit as x approaches negative infinity of this very same function. But remember that 1 over x has a behavior whether I'm going to the right or to the left, I'm always approaching 0, and this is essentially a translation 2 units up. So I end up with the 2 plus 0 again when I try and evaluate this limit, and so my horizontal asymptote is at y equals 2. And I wouldn't necessarily say that I have 2 horizontal asymptotes, because these are essentially the same line. If I were to imagine what this graph looked like, it would look like the 1 over x function that we talked about earlier, just translated 2 units up. So I'd have the line y equals 2 behaving as an asymptote, and the graph would approach it above in the case of the first quadrant, and from below for values of x that were less than 0. So that's our first example, but I also want to take a look at this example, which is a little bit more complicated. Notice that I've got x over radical x squared plus 1. And I need to deal with this, but I can't factor out an x out of this radical in the denominator. So what I need to do is I need to approach it from one of the ways we learned back in pre-calculus, and that's the idea of using a clever form of 1. I'm going to multiply the numerator and denominator by 1 over x. And if I do that in the numerator, this function becomes 1. If I do this from the denominator, I have to put this inside of a radical and really treat this as x squared. And so this becomes radical 1 plus 1 over x squared. So again, remember, to find horizontal asymptotes, I'm looking for the limit as x approaches infinity, and I'm also looking for the limit as x approaches negative infinity. But algebraically, my function y is the same as this limit as x approaches infinity of 1 over radical 1 plus 1 over x squared. And I know that this term goes to 0, so I have this ratio of 1 to 1, and so what I end up with is essentially 1 over radical 1 plus 0, or 1. So I could say I have a horizontal asymptote at y equals 1. Looking at my function, though, it's difficult for me to approach this from x approaches negative infinity by using this algebraic relationship. What I want to do is I do want to talk about the even or odd situations that we talked about in previous videos. Y equals x is really x to the first, and so that makes my numerator an odd function. In the denominator, I've got x squared plus 1, which is an even function. And again, if I was to look at this function, since this is never 0, and since it's never negative, I do have that y-axis symmetry here. So if I take an odd function and divide by an even function, I end up with an odd function. And if I have an odd function, I do have to have that rotational symmetry. So if I have a asymptote at y equals 1 for positive x values, then by the rotational nature of symmetry, I should have an asymptote, a horizontal asymptote at y equals negative 1 for values of x that are less than 0, in particular as they decrease without bound. So I'm using the behavior of even and odd functions in this case. So I can look at the horizontal asymptotes for a lot of different functions, including this function. So I've got the limit as x approaches infinity of sine x over x. And please note, this is not the limit as x approaches 0 of sine x over x, because we talked about that in a previous video that that's 1. What we need to do is we need to look at this from a behavior that we've talked about before. We know that the sine of x has to be bound between 1 and negative 1. This is something that we'll be using over and over for limits involving sine and cosine. This idea of being able to bound a trig function by its range and using the sandwich theorem to get functions that are a lot easier to work with. Because I don't have the ability to simplify this algebraically, this doesn't behave like any parent function that I'm used to, and I can't multiply by a clever form of 1 to eliminate the problem. I really need to take a look at this from a sandwich theorem point of view. So I know that sine of x bounds between -1 and +1, and so that means that if I wanted to look at sine of x over x, this function would necessarily have to be bound between -1 over x and 1 over x. So if I wanted to look at the limit as x approaches infinity of sine x over x, I have to be bound between the limit of each of these two functions, the limit as x approaches infinity of -1 over x, and the limit as x approaches infinity of 1 over x. And luckily, these two functions have very predictable behavior. This is our parent function we talked about. Whereas x goes to infinity, this function approaches 0. And because this is just a reflection across the x-axis, its limit is going to be the exact same value, in this case 0. So my limit has to be bound between 0 and 0 inclusive. And so that means that the limit as x increases without bound of sine x over x is 0. So the idea of finding a horizontal asymptote is necessarily finding the limit as x approaches either a positive or a negative infinity for my function. And we have several techniques. One, of course, is to try and look at it from a parent function behavior. The second is to use algebra to simplify. And the third is the sandwich theorem. All of these techniques we've talked about in previous lessons. And similarly, if I find a limit as x approaches positive or negative infinity, that necessarily is going to give me the horizontal asymptotes for that function as well. And notice I say horizontal asymptotes because I can have up to 2. I can have a horizontal asymptote for positive infinity, and the one for negative infinity may be different. So we need to be aware of that. So this takes care of horizontal asymptotes. The next thing that I'd like to talk about is vertical asymptotes. And of course, vertical asymptotes are where our domain doesn't exist. In other words, the limit as x approaches a particular value, either from the left side or from the right side, either increases without value or decreases without value. In other words, these limits will go to a positive infinity or a negative infinity, because that gives us the telltale signs of what we expect for a vertical asymptote, that it should go to a positive or negative infinity, possibly in the same direction. And we've seen these types of functions before in our pre-calculus classes. And of course, one of the functions that we deal with a lot is the tangent function. The tangent function, we know tangent is the sine of x divided by the cosine of x. And we know that this function is going to have issues whenever the denominator is equal to 0. In general, our vertical asymptotes occur when the denominator is equal to 0. And so what we need to do is we need to find out, okay, what values would make cosine equal to 0? And we know that x equals pi over 2 is one of our solutions. And odd multiples of pi over 2 are going to give me that as well. So 5 pi over 2, 7 pi over 2. And in general, that's that 2n plus 1 pi over 2 for integral n. And so we know that we're going to have vertical asymptotes at these values, where x equals 2n plus 1 pi over 2, where n is an integer. A more tricky problem is to think of it when we're looking at it from a solely algebraic standpoint. And again, I can deal with this algebraically because both of these terms factor. the numerator factors to x minus 2 times x minus 2, and the denominator factors to x minus 2 and x plus 2. And this is a situation that we were talking about back in section 2.1. The idea is that if I have a common factor in the numerator and the denominator, it's not going to give me an asymptote. It's going to instead give me a whole. In other words, the limit as x approaches 2 of my function exists. It is a finite number. But I am going to have a problem here because I can't eliminate that factor of x equals negative 2. And so I'm going to have this issue where the limit as x approaches negative 2 of my function is either going to go to positive or negative 0. So it does not exist. And so that means that we have a vertical asymptote at x equals negative 2. And we have a whole at x equals positive 2, a removable discontinuity, a place where the limit exists but the function's just not defined. So again, we do need to be aware of what we talked about in section 2.1. If I can algebraically eliminate a factor so that that factor no longer exists in the denominator, it's not going to give me a vertical asymptote. It's going to give me a whole. It's going to give me a place where the limit exists, but the function itself is not defined. So, I want to touch on a few things here. We talked about horizontal asymptotes. And in the case of our function that we dealt with, the sine x over x function, this function can cross our horizontal asymptote an infinite number of times. And some people think that asymptotes are lines that are never crossed. That's not true in the case of horizontal asymptotes. Horizontal asymptotes can be crossed. And the reason they can be crossed is because we're talking about what happens at x equals positive infinity or x equals negative infinity. We're not talking about the behavior on the way there. We're talking about what we expect out at that distant point. So we're still talking about values that are in the domain. These points are values that are in the domain because there's nothing wrong with dividing by non-zero numbers. If I'm looking at a vertical asymptotes cannot be crossed. Because when I look at a vertical asymptote, I'm talking about a place where the domain is not existing. I'm talking about a place where that x value is not an eligible value to be substituted in. So because I'm talking about a break in the domain from all reals, there's nothing to substitute into our function. So a vertical asymptote, because it's not a part of our domain, it can't have a point, and therefore it cannot be crossed. Horizontal asymptotes are not excluding points from the domain, and so horizontal asymptotes can be crossed, and in the case of our sine x over x function, can be crossed an infinite number of times. We'll notice this for periodic functions that have horizontal asymptotes, that they can be crossed many times. Even though we're used to functions like y equals 1 over x, where a horizontal asymptote is actually pretty protected. There is no value for my function where y could be equal to 0. And that's not the case for this function over here. So it's just something to keep an eye on, something to take note of when we're talking about the difference between horizontal asymptotes and vertical asymptotes. So once again, this is Mr. Potter. Thank you for watching. Have a great day.